semester. We are very excited to have Brian Swingle give a talk today. He's from Untitled and he's worked on various different topics. And today he'll talk about quantum chaos and hydrodynamics in random matrix theory. Thank you for being here, and please go ahead.
Great. Yeah. Thanks a lot for the invitation. Nice to see you all. Wish I could be there in person, but this is my tribute to the locale here on my first slide. There will be a lot of Hamiltonians in this talk, so seemed appropriate. Yeah, and like I said, I'm very happy to be here. I pitched the talk pretty broadly, but of course, please stop me and ask questions at any point if you have them. I'm very happy to discuss anything in more detail. Yeah, the subject for today is going to be quantum chaos, and I want to tell you about developments in that field. It's an old field, but there's been a lot of recent developments, including developments coming from ADS-CFT, from quantum gravity, from the quantum physics of black holes. And that's part of a set of developments that have really reinvigorated the field. And now we're thinking through again what we mean by this term, what the physics we want to associate with quantum chaos is, and what are the different manifestations. And today is kind of going to be about talking about different manifestations of a not completely precisely defined notion of quantum chaos and how we can connect them and move towards a bigger picture for the subject. Okay, so let's get started. I want to start by talking about the puzzle of irreversibility. So this is something that we're very familiar with. Quantum systems display irreversible behavior all the time. Everything from heating and entropy growth to relaxation to equilibrium. Even diffusion, like dissipative transport of charge and energy, can also be viewed as an irreversible process because it creates heat. And in the context of black holes, the information loss paradox or puzzle is, of course, a famous manifestation of this apparent irreversibility. Yet, as we all know well, the microscopic dynamics is perfectly time reversible. It's just the Schrodinger equation there with the Hamiltonian. And this is not a purely academic question, going back even to the 50s in the spin echo work of Hahn, which I show an experimental plot here. He found that you could actually effectively reverse the dynamics, at least approximately, and see these very dramatic revivals in the magnetization signal of some spin sample, right? So there was still some overall decay, and we can talk about that later. But you could essentially revive the signal, you could reverse time, so to speak, and really see the coherence reappear. Okay. So, how do these two things interact, and where do you get this irreversibility out of the apparently reversible microscopic dynamics? Now, a very common thing to say is, well, you take your system, you couple it to a big bath or a big environment. I mean, that's certainly true for any quantum system we have. It's coupled to a big universe. And the claim is that this bath or environment can rationalize or justify the sort of irreversible behavior that you see, because you have some non-equilibrium state where entropy or information is flowing out into the environment, never comes back. And that can give you a source of irreversibility. And that's definitely true. I mean, this bath environment is definitely generically present. But I want to claim that it doesn't really fully address the issue. I mean, for example, if you re-include the bath in your microscopic description, then you have the same in principle issue again. And even if the bath remains out of equilibrium for any accessible time scale, you can still ask the question how subsystems of this big bath system composite, namely the system itself, how they look like they are approaching equilibrium, for example. That's not a completely trivial question to answer or to give an explanation. Now, I would say more directly, a lot of developments in quantum control have actually given us access to many body systems that are effectively isolated over many microscopic times, right? So we can actually directly probe this physics in an approximately isolated setting, and still we see all these hallmarks of irreversibility. So it actually is a real experimental question where there really isn't a bath, at least not on some kind of reasonable time scale. There really isn't an environment, and still we have irreversibility, so still we want to understand that. And even if perfect isolation were always an idealization, I'd like to argue that it's really extremely useful to think through these conceptual issues regardless. And I'll give you two examples of that, where we really want to understand how irreversibility arises. The first example is something that's kind of dear to my heart. I started life doing condensed matter physics, thinking about strongly correlated electrons. And there, a very classic kind of experiment that you can do is a transport measurement. You can measure the flow of energy or charge. Typically, charge is easiest, but you can also study energy. And the baseline situation is that for a wide variety of strongly interacting systems, we just don't know how to calculate the observed transport properties. So on the right here, I'm showing you just a prototypical phase diagram of what's called a high TC superconductor material. The details are not, this is just sort of flavor text, but you have lots of different electrical resistivities, rho, that's what the rho stands for here in this diagram. And in particular, in this gray region, you have a resistivity proportional to temperature, which is, if you look at the theory of metals, very hard to achieve at low temperature. It's an unusual kind of resistivity. And we really don't know where this comes from, and we don't have a good way of calculating it, right? And it's not just because we don't understand like microphysics, like even in some totally well-defined model, like the Hubbard model, say, or some other lattice model of the physics, we just do not in principle know how to calculate this transport property. It's not like we need a bigger computer. It's like from a classical point of view, from any kind of classical computation, it's, as far as we know, extremely hard to carry out, right, in general. So it's a really big puzzle. Now, as part of this puzzle, we know that hydrodynamics is supposed to govern the long wavelength physics, ultimately. And here I put hydrodynamics in quotes because I'll call something even as simple as diffusion effectively like a kind of hydrodynamics. I'm using it in this generalized sense of the word where it just refers to the kind of long wavelength effective theory of the slow modes. And so, we know that or we think at least, hydrodynamics governs the physics. But in that context, the way to state this hardness is to say that it's hard to compute the transport coefficients. That it's hard to compute the parameters of that effective field theory from the microscopic model. And part of the issue is that we don't actually really fully understand how hydro emerges from the microscopic theory, because hydro is itself a dissipative process, at least once you go to higher orders. It's a dissipative description, and so you need to understand again how dissipation is arising and how you're making that transition from this microscopic quantum world to this effectively classical description. Now, another situation where this kind of irreversibility is very acute is in the case, again, of black holes. Here I show you on the right some data from LIGO, where this little final decay from the big wiggles down to the small wiggles is actually the ringing down of this black hole with its quasi-normal mode. So it is actually relaxing to some kind of equilibrium configuration. And these quasi-normal modes, the event horizon, the information problem, these are all, again, manifestations of apparent irreversibility in this system, right? And although we don't really have access to the quantum dynamics of black holes yet experimentally, it is a key playground conceptually for thinking about puzzles of quantum gravity. And so here too, I'd say we'd like to understand much more deeply how irreversibility arises. Now, what's the big picture here? I claim that these are all different avatars of what I'd like to call quantum chaos. And as stated here, it's a somewhat vague term that encompasses lots of different phenomena or manifestations. And one of the major goals in the field is to move towards a more unified picture of what quantum chaos is and how its different pieces are related to each other. So here's a kind of visualization of that. I would say my interpretation of the older literature is that quantum chaos started really as asking the question, what are the quantum manifestations of classical chaos? There was, for example, an argument sometimes raised that, okay, the Schrodinger equation is a linear equation, so it can't have chaos in this classical sense because it doesn't have nonlinearities. And so you just can't have chaos in quantum physics. Now, I think that's actually a wrong analogy, that the right thing to do is not to look at the Schrodinger equation, but the dynamics of observables, which still can be effectively nonlinear. It's like saying that in classical physics, the dynamics of the phase space probability distribution, which is governed by Liouville's equation, is also linear, so you can't have chaos, but that's obviously false. But nevertheless, there was a big community of people who spent a lot of time thinking about how classical chaos manifests in a corresponding quantum system. Like if you were in the semi-classical limit where your quantum effects were there, but you had a big Hilbert space, h bar was small in some sense, what were the signatures? And there are many famous signatures. For example, it was observed that the energy levels of the quantum Hamiltonian looked like the energy levels of a random matrix. This goes all the way back to Wigner's observation about the structure of nuclei. Other features were that such systems would thermalize in a certain sense, like they often had diffusion and they would equilibrate in a precise sense. But this kind of tying of the idea of quantum chaos to some kind of classical limit or to classical chaos, I think is just philosophically wrong, because as far as we know, the universe is fundamentally quantum, not classical. So we ought to have a fundamentally quantum notion of quantum chaos, And maybe we should use a different word. Maybe chaos should be reserved for something else, but where the field is now, we're kind of stuck with this idea that there should be something called quantum chaos that in some sense limits to classical chaos in the appropriate regime, but is a more basic notion. And I emphasize this is not just a philosophical question, because there are plenty of quantum systems out there that don't have any kind of sensible semi-classical limits, but where we still have many of these manifestations. And we'd like to have some overarching notion that describes what's going on in that collection of systems. And so again, we're pushed to formulate some notion of quantum chaos. And so what are some of these manifestations? I'll go through some of them in more detail in a second, but they include things like a Hamiltonian, which looks like that of a random matrix in some sense. They include ideas of thermalization, of hydrodynamics. They include ideas of complexity growth, so that quantum states become more complicated as a function of time in a definite way. They include ideas that eigenstates, energy eigenstates, also look random in a certain precise sense. That's what we'll call eigenstate thermalization. And then a relatively recent development in the area is the idea of information scrambling. And this also makes sense from the point of view of chaos as a kind of pseudo randomness. It's like as random as you can get with a deterministic evolution. And that's kind of what's going on with information scrambling. It's about taking information that starts simple and becomes complicated but still in a deterministic way, right? So you're not really randomizing it in a truly random sense, but it's some kind of pseudo randomization or hiding of information in complex degrees. And my vision, at least, is that we have ultimately some unified picture of something called quantum chaos, which incorporates all these different features together in one big framework and explains, do they all co-occur together? What are the different time scales? What are the conditions? Is it possible to have some without others, and that sort of thing. And as I hopefully motivated on the previous slide, I think this kind of understanding is also going to help us to answer questions we care about independently. For example, questions about the physics of transport and questions about the physics of black holes. So let me give you a little bit more in-depth preview of what I'm talking about here. I'm going to focus on 3 subjects in this talk today. I'm going to focus on information scrambling, on hydrodynamics, thermalization, and this random matrix structure. And I'm going to try to actually show you a plausible trajectory where we start from scrambling and get all the way to random matrix-like behavior at the end of this talk. So that's kind of the goal. So to connect these 3 pieces together. So let's start with scrambling. What does this mean? Well, it's a sort of simple-ish idea. Like, the basic thought experiment is you write a note or a bit string on a piece of paper. You throw that into a fire. You let the fire burn out. And then we think that dynamics is reversible. So in principle, the information that you wrote is contained somehow in the ashes and smoke and whatever detritus from that fire. But you're not going to be able to figure out what the message was unless you have some kind of complete and total control over the system and the ability to perform, insane calculations and measure ultra tiny effects and all kinds of science fiction like abilities that we just don't have. So the information is effectively gone, even though in principle, we think according to the laws of physics that it's still there. And that's a classical example, but this thing happens in the quantum world as well. Here is a prototypical quantum chaotic system by various definitions. This is a quantum spin chain. So just think about a one-dimensional chain of spin halves. Doesn't really matter what they are. They could be electrons, dependent in position in some locations, but let's just think about them as quantum spins. And there's some interactions here. The system has a ZZ coupling, which in the ground state would favor the spins to align on the Z basis. And then there are also magnetic fields in X and Z. And importantly, Z and X don't commute. So this Hamiltonian is non-commuting and has some non-trivial quantum dynamics. And in particular, if I add this Z term here, without the Z term, it's actually an integrable system. It's equivalent to non-interacting fermions. But with this extra Z term, for generic values of the coefficients, we believe this is a quantum chaotic system. Okay. So I'm going to take this system as a prototype and show you just visually and mathematically how we characterize these different ideas. And we're going to start again with scrambling. So let me encode some information in my system. I'm going to do it the following way. I'm going to start with a state which consists of all plus y eigenstates of these spins. I choose y because every term here has 0 expected value in that basis. So the average energy in this state is just 0. And that's right at the middle of the spectrum. So this would correspond in your microcanonical thermodynamics to an infinite temperature state, which is right in the middle of the spectrum. And then I'm going to consider another state, which just obtained from the first state by flipping the first spin from plus y to minus y. And that's what's here. So this is just a simple local spin flip. I'm encoding, if you like, 1 bit, or if I consider arbitrary superposition of these states, 1 quantum bit of information in a local way into my system. Right. Now I'll let time evolve, and I'll ask, okay, let me look and see what's, say, the expected value of that first spin as a function of time. Here I'm plotting time in units of 1/j, and the expected value, and you see for state 1, where it was initially plus 1, starts here, then it drops, it kind of oscillates and it wiggles, and then at late time it looks like it's around 0, which is what you would expect in equilibrium at this energy. And then for the state where it was -1, it does a sort of opposite oscillation, again kind of damps out, wiggles, and then if I looked at this late time region, you would have a hard time telling me where I started with state 1 or state 2, because the wiggles are almost the same. But I assure you I'm doing the numerics right here, and this is a perfectly unitary evolution. It's just that this simple observable can't tell these two states apart anymore. And I claim there's nothing particularly special about the spin of the first particle. If I looked at any other like single spin measurement or 2 spin measurement or even 3 spin measurement, I wouldn't be able to tell these two things apart with any reliability. What I need to do is actually make some complicated, specially tuned multi-spin measurement. And that could then tell them apart, but that's very hard to do. It's not what we typically do in experiment, and so we have effective information loss. Now, this lasts a long time. Here, I'm just showing you the same thing, but out to 1,000 time units. You can see compressed to the initial time, this decay. And okay, there's like lots of fuzzy wiggles. There's some finite size effects. These would get smaller if I made a bigger system. This is only 14 spins. So I don't need a huge system to see this physics. And this would get smaller if I considered more spins. And you see it just kind of lasts forever. It doesn't seem to recur or do anything crazy. In fact, just for fun, you can go and write a little computer code that searches for the actual quantum recurrence time as a function of system size. So you start in some state, you ask how long it takes to come back to that state with relatively high overlap. And this is the recurrence time, the blue as a function of system size. Don't worry about the red curve. That's just some kind of theory prediction, but the blue is the numerical data. And what I'm plotting here is system size versus the log of the time. Okay, so that means the recurrence time is e to the system size, which is a very, very big time. And actually, even at size 6, I didn't have enough patience to wait for the code to run. Like it would take days or something. I don't know. It would take a long time. So it's roughly linear. Basically, the recurrence time is so long that for any practical size system, you can just completely forget about it. So for all practical purposes, the information is scrambled up, it's hidden, it's unobservable, and it never comes out again. Okay, that's scrambling. Now, this system also exhibits hydrodynamics in the sense that I said before, just some slow modes, in this case, diffusion of energy. The reason why you have diffusion and not, say, sound is because there's a lattice, and this is high energy compared to the lattice scale, so translation symmetry is broken. You only have discrete translation. And so if you just go through usual effective field theory rules, you expect just diffusion, not just one slow mode, and that's what you see. But again, it's actually not known. There's no sort of principled known way how to, well, that's too strong. I would say we do know sort of now, or we have good guesses, but a priori, it's not obvious how to calculate the transport properties of that model. It's not an equilibrium calculation. It's not something you can do in Monte Carlo, for example, reliably at large size. It really needs big size and long times, and that's hard to achieve. But as far as we can tell, it does have diffusive transport, and I'll explain to you later in the talk that we now understand or have a good idea how to actually calculate, and we can get physics that we expect. Okay, so this is the diffusion constant of energy as a function of temperature and units of the gap. And I'll explain the physics behind this plot a little bit later on, but just to show you that we can do a calculation, it does diffuse energy, it does diffuse, and we moreover can understand and calculate that diffusion, and it makes sense with our microscopic understanding of physics, as I'll discuss in more detail later. And then I can also look at the energy levels of this Hamiltonian. So here again is my Hamiltonian now with 8 spins. So there's 256 levels in this Hamiltonian. And on the right, I show you in this kind of barcode-like plot, the energies as a function, the levels as a function of energy. So you see down here at -15, there's something like a ground state, which is kind of separated from the rest of the spectrum. It's a relatively special state. There can also be some highly excited states up here that are also relatively special. But most of the states sit in the middle, and they look like this sort of featureless jumble of lines, right? There's not a lot of structure here. If I had considered an integrable system, you would see a lot more structure just visually, even without taking any kind of quantifiable measure of the randomness into account. And so what I claim is that this Hamiltonian has random matrix-like levels in the following sense. If you modify it to define an ensemble, say add a small random magnetic field in the z direction, it doesn't have to be a big field, just a little bit to make it have some random spectrum, then in a certain precise quantifiable sense, the levels of that ensemble of Hamiltonians will look like the energy levels of our random matrix at sufficiently late time or sufficiently fine-grained level space, like energy difference.
So you mentioned that for integrable system there will be more structure. So how is the transition if you slowly turn on the non-integrability constant? Does it suddenly shift the energy levels, or does it sort of slowly get random?
Yeah, this is a really good and deep question, which I don't think we have a consensus on. The simplest, I would say, behavior is that in a thermodynamic limit, if you take thermodynamic limit first, it turns on suddenly. So like if you take an integrable system and you add a small and non-integrable but like intensive perturbation, then it would just immediately become random matrix-like at long time in large systems. But there can be interesting crossover as a function of system size and time. And it's also possible by analog with the classical Can theorem that there could be some sort of resilient non-integrability that may be present that we just don't know about. That's actually an open question, I would say.
I see. Okay, that's interesting. Thanks.
Yeah. Okay, and yeah, and so again, this kind of idea, it goes back at least to the work of Wigner with nuclei, but then it was kind of codified in the quantum chaos literature by this so-called BGS conjecture that the energy levels of a quantum chaotic system are always random matrix-like. So those are the 3 things I'd like to connect together today. And as I said, I'm going to try to show you how information scrambling can be understood as giving rise to effective information loss, effective dissipation, which can help us rationalize hydrodynamics and actually even helps us calculate. And then I'll show how hydrodynamics, formulated as a fluctuating effective field theory, predicts this random matrix behavior. And thereby we connect these three things together and sort of say that, well, at least as far as those three things are concerned, quantum chaos is a more unified notion that has these just three different manifestations that come together. Okay. So let's go back again to our two states, which are evolving in time. And as I noted in that slide, there is a simple operation at time 0 that turns one into the other. That's applying, say, a Pauli Z to the first spin that flips plus y to minus y. And you can say, well, if you want to do that change, if you want to convert one state to the other at later time, you should do the following thing. You should just rewind time on the first one, apply the spin flip, and then fast forward again back to the moment in time you were at. Right? And that's actually exactly the kind of thought experiment that's encapsulated by the so-called Heisenberg operator. Here I've put the forward and then the backward, but it doesn't really matter. And you can think of this as like a kind of version of the butterfly effect thought experiment. You know, in that thought experiment, you start with two nearby points in phase space and you watch them diverge. You could equally well think about starting somewhere, going forward, making a small perturbation, and then going backwards. And if you didn't make a perturbation, you go back to where you started from. But if you do, then you actually diverge quickly to some new location because of this small perturbation. So you can think about sort of like the same kind of thing happening here. You're going forward, you're making a small perturbation. W could stand for the wing flap of the butterfly. And then you're going backward and you kind of see where you get, right? And if there were no perturbation, you just return to your initial state, or you'd have a do nothing operation. But if there is a perturbation, then the perturbation can grow. So here's a space-time picture of that. Space is on the x-axis, time is on the y-axis. Each of these black lines is the world line of a qubit. And I'm going to think of the interactions as coming from these little blocks. So think of this as just like a sequence of two-body interactions or some kind of trotterization of that Hamiltonian dynamics. The details are not super important. Just you can always think about the evolution this way. So these little orange blocks could be like that ZZ coupling, and then you could also include within them the fields as well, which do little rotations on the spins. And these orangey blocks are going to be forward, the purple blocks are backward. And the property of unitarity is if you go forward and then go backwards, that you can just cancel the evolution completely and you're left with nothing, right? But now if we put our butterfly in there, our little perturbation, we try the same kind of cancellation thought experiment. You see in the first attempt to cancel, most of the couplings cancel, but the ones that contact with the actual perturbation don't necessarily cancel anymore. Like this is now some more general unitary acting on two qubits. That's not the identity, right? So let me just color it blue. It's some generic thing. Now it's on two qubits instead of just one, and it's there. Now we can cancel the next row, and again, most cancel, but now there's an additional non-cancellation, right? You keep doing this, and you see that the perturbation, every time you apply a layer, which is every step of time, grows in space more and more and more. Right? And so what this represents is the growth of perturbations under time evolution. It's saying, you know, how different is state 1 from state 2 as a function of time? Well, the difference will be supported on the support of this Heisenberg operator. And we can actually measure that support using commutators. For example, you can put some other probe operator into the system and ask whether the operations commute or not. That'll tell you whether the perturbations has spread to the location of your probe or not. And you could look first at the expected value, for example. That's actually familiar from linear response, and it turns out just to vanish for the same reason that information is lost at late time. So expected value of the commutator is not a good measure of this quantity, but then you look at the second simplest thing, which is the square, and that doesn't vanish. And if you've heard about out-of-time order correlators or any of that stuff, that's just kind of the non-trivial term in this so-called squared commutator. So I like thinking about it this way because I think it's a very physical, visual way of seeing why you would care about these out-of-time order correlators or OTOCs. They're just reflecting the growth of operators according to the picture I showed you before. And the reason why you need them is because the operator, the commutator is, say, non-trivial, but its diagonal matrix elements are small. That's reflecting information loss. But the off-diagonal matrix elements are not small, and this squared object lets us measure this. And so I just want to comment that you can actually do experiments with this. This is an experiment that Paolo Capollaro's group, in collaboration with Horacio Pastalski's group in Argentina, did on a material called Adamantine. So this is a system where you have these molecules with 16 protons, each of which has a nuclear spin. And these molecules are nearly spherical, so they actually form a FCC lattice in their solid state, but because they're so nearly spherical, they tumble in real time in this lattice. It's a pretty exotic kind of thing. So you have these like molecules with nuclear spins on them tumbling in place in the lattice. And so what you get is a very interesting kind of nuclear dipole-dipole model. You have these dipole-dipole interactions between different spins, and also in the presence of a large Zeeman field. So this is a standard kind of nuclear magnetic resonance experiment setup. And they have developed technology over the years, actually going back to the 70s with something called Magic Echo, to effectively reverse not only the single particle evolution, which is what Hahn did in the 50s by applying these magnetic field pulses that flip the spins effectively. Now they can actually reverse even the many body evolution, approximately, using the special properties of the dipole-dipole interaction. I'm happy to tell you how that works, well, now or later if you care, but it's a really cool technique that they've been doing since the 70s. So actually, I like to say, tell people they've effectively been measuring these out-of-time order correlators or some cousin of them for almost 50 years, which is pretty cool. But the connection between what people in the theory community had been calculating and what people in the MR community have been measuring had not been made until relatively recently. And in particular, what they can measure are actually global commutators, so not commutators of local operators, but of total operators, like where you sum up all the spins together to form the total spin. Because in MR, as you may know, they have no local accessibility. They can't like locally image things. They just measure the total response. But recently, with a postdoc at MIT, Tianxi Zhao, we showed that actually this object relates to the original local OTOC by just integrating it in a certain precise way. It's like the area under the curve of the local thing, in such a way that you can convince yourself that this global quantity should just be the butterfly speed, which is that speed of expansion of the perturbation, times time to the dimension of the system, right? At least for a local system. And then actually with dipolar interactions, it turns out it's more complicated because you have power law couplings, and that can speed things up. And we actually predict theoretically, using a random circuit model, that they should observe superballistic growth of operators. And that's an interesting another story, which I don't have time to get into right now. But let me just say that they can do the experiment. They did the experiment, and they actually measured this global OTOC. And they're plotting here for some reason the square root of it. I won't explain that, but just square it in your head. And you can see you get up to a value of about 10 to the 4. So that means the very little interpretation is that this local operator has actually spread to 10 to the 4 other sites or other operators. So you really are experimentally measuring this spreading of perturbations via these nuclear magnetic resonance echo-like experiments. And okay, in theory land, we can actually make models of this, and we can reasonably well match the data. That's what this dotted black line is here. The colored dots are the experimental data. So we can match the data qualitatively, and we have sharp predictions for if they can go to longer times. But the basic takeaway is that this operator growth is a real thing. You can actually see it in an experiment. And it's, as far as we can tell, a totally generic feature of what you might want to call quantum chaotic systems, right? So operators start simple, they become complicated.
Actually, sorry, can I just ask about the theory prediction for
Sure.
this? Is it like, do you generate that curve numerically, or are you able to? So I presume this is some sort of exponential thing. And are you able to like analytically predict the coefficient, or do you just numerically compute it?
Yeah, that's a great question. So what we can analyze most easily are what are called random circuit models.
Yeah.
So this is a model where you preserve the power law character of the interaction, say that 1/r³ character of the dipole-dipole interaction, but with like a white noise coefficient in the Hamiltonian, so the time-dependent Hamiltonian, and we can actually analyze that exactly by mapping it to a master equation and solving it, including analytically in many cases.
Okay.
And yeah, so this little picture here, which I didn't explain, is a phase diagram, which you can obtain analytically. And the alpha is the exponent of the interaction. So in 3D with dipoles, you have alpha equals 3. And this says that if alpha is bigger than 3 plus a half, then you have ballistic motion. If it's between 3 and 3 plus a half, you have some like stretched power. If it's exactly 3, you get some really exotic behavior where it's like not quite exponential with time, but some like e to the log time squared, like something really funny. And then if it's small enough, then you can get exponential growth, which is like an all-to-all model. Okay. It's also related to models people considered in the like biophysics or speciation literature, like where you have spreading of species with like the possibility of long-range jumps, which are power law suppressed.
So then also when you say you sort of match it to the data, then there's sort of some sort of, you're assuming some sort of universality, right? So that these random circuit models are somehow capturing the whatever like complicated molecular physics that's going on.
Correct. Yeah, that's right. So yeah, to be precise, in this paper here, for example, with my collaborators, so Andrew Guo is my student, Shenglong Xu is a former postdoc, and then Tianxi is a postdoc at MIT, and Xiao Chen's a professor, junior faculty at BC, Boston College. In this paper, we analyzed this random circuit model and also did some numerics and spin chains to substantiate the claim or the idea, which also had some heuristic argument that this behavior would be universal at long time. And you have a phase diagram only dependent on the power and the dimension of space. So that's a conjecture that we made, and we don't know if it's true or not, but it seems pretty reasonable at least. At least that should be a big universality class where many systems fall. The thing about this experiment is they only go to quite short time. So they basically go to 1 inverse coupling time, which is certainly far too early for me to really argue that it's universal. I mean, the short time regime, all the details can matter in principle. So what's actually here is just a stochastic model with 16 point dipoles on the sites of an FCC lattice where we just literally simulate the model. And there's 2 fitting parameters. There's the time scale and the offset of the time. And this is just the best fit with those 2 parameters. The experimentalists also produce a fit where they fit a power of time and a coefficient. So they have the same number of fitting parameters and can get a similarly good fit. So I don't want to claim that it's like really definitely what's happening at this short time scale. Just that it's qualitatively right. Like you can just do a rough estimate of how big you expect the number of spins to be, and it roughly matches just by taking the actual experimentally measured dipole-dipole coupling. But the details are not something I would claim that we fully understand. Okay, so let's talk about hydrodynamics now. Just to remind you, with a little bit more of an equation, we have this picture of irreversible flow of information. Again, irreversible up to 2 to the n kind of times, where we start with a simple operator and it becomes very complicated. And we can think of it mathematically as the following thing. You can always take any operator, which is, let's say in this case, my expanding perturbation, And I can expand that into complete basis of operators obtained by tensoring polys on every site. You know, in a quantum field theory, you can imagine something analogous to this, but it's harder to write down. So that's why we like to think about things in this sort of spin language. And there'll be some amplitudes that change in time, right? And the basic point is that there are many more complicated operators, many more operators with many polys than few polys. In fact, the typical operator has about 3/4 of the sites with a non-trivial poly on it, because there are 3 non-trivial polys and 4 operators, identity X, Y, and Z. So you would expect at late time in some generic sense for this operator to be concentrated on very high weight operators, which you can easily convince yourself are not accessible to any simple experimental probe. So if you make any simple measurement, you won't be able to detect if this operator has some component which involves, you know, a significant fraction of the system having some poly operator. So the basic idea is you evolve from simple operator to complicated operator, and that explains the irreversibility, or that gives you a very concrete manifestation of it. And with one exception, which is that if you have a conserved quantity, like say energy density, which I here denote epsilon of t, then part of that dynamics is protected, because say the sum of all the energy densities has to commute with the Hamiltonian, it's just the Hamiltonian itself. And so for these conserved quantities, there should be some special component which evolves slowly because of the constraints from energy conservation and locality. So you might think that you could decompose the general operator into some, what I'll call hydrodynamic part, which is like the slow stuff, the special protected stuff, and then this more generic complex part. And the idea of how hydrodynamics can emerge in this picture is then that, well, this hydro part is generic, it's determined by the symmetries, its structure. And so it should essentially obey the equations of hydrodynamics, which are determined by the same set of data. And this complex part of the operator is, as I said, complex. It becomes kind of unobservable. It becomes very, very supported on very high weight polys, and essentially sort of plays no role in the late time physics. Right? But we can do better than that. We can actually say, well, you know, suppose we could sort of throw away this complicated part and just work with the hydrodynamic part of these operators? Could we actually calculate something? And there are ideas along those lines as well. I'll just show you one of them here. One of the ideas, let's take this system and couple it to some explicit heat bath, say on the left and the right. Here's a temperature T left that's hot and the temperature T right that's cold. And if you couple your unitary spin chain to this open system on the left and the right, and you imbalance the temperatures, then heat will flow from the left to the right. So you'll have an energy current. And this open system dynamics can be viewed as like a trick or an escape valve, a pressure release for all this complicated stuff. It gives you a way to kind of throw it away effectively by coupling to this environment, even though the chain itself is still unitary. And so from this point of view, you might say, well, maybe we can actually represent at least the hydrodynamic parts of the evolving quantum state or evolving operator using some efficient classical description. In this case, one thing we can do is to use what's called a tensor network. So we could think of this time evolving quantum state, which is just a Schrodinger picture version of the time evolving operator, as being constructed out of a tensor network where each blob has an input and an output physical leg. That's because of the density matrix, it's an operator. And then some virtual indices here that encode entanglement or correlation between the different parts of the system. And it's a standard fact that if you look at the whole operator or the whole state, it will be very hard to encode this with the tensor network because you have very high amount of entanglement, very high entropy. And so there'd be no way you could encode this as a simple tensor network. But if you only care about the hydrodynamic part, which is this simple, special, protected part, then you can argue that, okay, maybe the state looks locally like it's in thermal equilibrium, and maybe actually it should have an efficient tensor network representation. Right? In fact, we made such an argument using some information theory tools, but just think of it as an ansatz. And so then you can try to solve the dynamics with these heat baths as a way of generating the current within the space of these simple tensor network states, which are designed to capture the hydro part and ignore the complicated part. So with my student, well, not my student, but a student, he was an undergraduate who worked with me, Chris Zanocci. We actually did this for the Hamiltonian I showed you before, in the regime where the temperature is small compared to the energy gap between the first excited state and the ground state. And in that regime, let me just tell you quickly what you expect physically. You're going to have a dilute gas of quasi-particle excitations. It's like a quantum field theory where the mass is much larger than the temperature. So you just have some dilute gas of excitations. They have some collisions, which can be quantum, but otherwise they're basically a classical gas. And a special feature of 1D is that because of energy momentum conservation, two-body collisions are not sufficient to relax energy currents. That's a special property of one dimension. So you actually need three-body collisions to relax the energy current. So you can do a little kinetic theory and say, well, what do you expect for the energy diffusion constant in kinetic theory? You should expect that it goes like the density of excitations squared, or 1 over the density squared. And that gives a sharp prediction for an exponential factor because the density is set by the gap or the mass divided by the temperature. That's an activated behavior. And this power of 2 is set by the fact that this is 2. It's a 3-body collision. So you need 2 particles in the same place instead of a 2-body collision. And this factor of t is set again by like just looking at the velocity. Right? So the important point here is just that we have some a priori physics expectation in this regime of what the answer should be. It should have this activated behavior with a specific coefficient 2 related to the gap between the first excited state and the ground state. So we solved that problem. There's again the spin chain I showed you before with somewhat different parameters. We use this tensor network method with the open system to solve the dynamics. And we find that as a function of delta over t, if you plot the diffusion constant on a log scale at large delta over t, you exactly get this linear growth that I showed you on the previous slide with the exact coefficient of 2. So there's no fitting here at all, actually. We just solve the equation, the Lindblad equation numerically using the tensor network, and we extract the gap from like finite size numerics, and the factor of 2 is just 2. So there's no fitting. We just 2 new calculations and they perfectly agree. So the moral of the story is, not that this is the most interesting regime of dynamics for this problem, but that we've apparently understood the physics well enough that we can design an actual technique or procedure for calculating diffusion constants, which in this case perfectly agrees with our expectations from some other reliable method of calculation. And since this open system tensor network method was sort of based on some good physical principles, based on scrambling and understanding of equilibrium, there's a reasonable chance that it's more broadly applicable, right? And so maybe we actually now have one, and in fact, there are other methods along the same lines. We actually now have a set of methods where, at least in one dimension, we could actually calculate reliably the transport physics in these quantum chaotic models. And the insight actually came from thinking about the way information evolves in this system. So it actually relied on, indirectly on some quantum information ideas to ultimately make progress. Okay. Yeah, question?
Yeah, maybe, I think I may have missed this a little bit, but so the diffusion constants, they don't depend on the parameters of the microscopic Hamiltonian, or they do?
They do, yeah, they do.
And you can find that dependence? Or
You can find the dependence.
I see, okay.
So you can vary these parameters here.
The J, H.
The J, the H, the 2 H's.
And
as long as you stay away from integrability, this will work and give you a reasonable answer. And you always have diffusion, and you can calculate how everything depends on everything.
I see. Okay. Thanks.
Yep. So yeah, in the last little bit, let me talk to you very briefly about statistics of energy levels. And I'll first mention the precise mathematical way that we diagnose these statistics, which is using something called the spectral form factor. You can think of this in the following way. if you had a bunch of random numbers, which are these energy levels, the simplest that you could look at would be the expected number of them in some window. That's like the density of states. That turns out to be very non-universal. So I mean, it's still interesting, it's physically important, but it's not very universal. It's like different random matrix ensembles can have different values of that density of states. So it's not a very sharp signature of random matrix behavior. It's something that you can tune easily. By contrast, if you look at the correlation between pairs of levels, that is, in many random matrix ensembles, quite universal. It's given by the same structure, which depends only on the symmetry of the random matrix. And so the spectral form factor is essentially that pair correlation of energies, but Fourier transformed to the time domain. The reason why time is nice is because we have all these intuitions about time scales of thermalization and scrambling and so forth. So actually these times denote important energy scales via Fourier transform in the spectrum, but it's very convenient to think about things in the time domain because it matches some of these other expectations that we have. So this is what's happening here. We're taking energy levels EI and EJ, a pair. The overline denotes average over an ensemble. So we're just looking at the energy levels EI, EJ, we're averaging them and we're doing a Fourier transform. That's all this quantity is. And then the Fs are what we call filter functions. They help us look at like parts of the spectrum if you want. Like you can think about just a certain energy window or make them Boltzmann factors, or there's various reasons why you consider different filter functions. But the simplest thing for our spin chain is just to think about putting F equals to 1, which just looks at the whole spectrum and says, is this whole spectrum, does it have a pair correlation of energies, which is like that of a random matrix or not? That's the basic question. And the random matrix behavior is that after some short time, this spectral form factor is just linear in time. And if you go and compute this quantity for the spin train I showed you before, you actually find this for the appropriate time window. Okay, so it is a random matrix, like it even has the same coefficient. And what's in this picture here is just a visual representation, or sort of like a path integral kind of representation of the object, where we have a forward contour and a backward contour. We square that quantity, we take a trace, and then we average it. Okay. So because the it looks similar to the butterfly effect situation again, where we had a forward and backward piece, but now we've kind of gotten rid of the detailed operator and we're just looking at the sum over all states, which is a little bit more universal than object. But it actually still knows about the slow physics, as I'll convince you in a second. So this is the mathematical object we consider, and this linear in time piece, which is called the ramp, is the signature of the long range level correlations in a random matrix. Here's what you get in a little bit more detail. I won't talk in detail about random matrix theory, but you have essentially, for a class of problems, you have, say, a random matrix in the form of matrix elements, and you have some potential, which in this case is unitarily invariant, say. So it boils down to a probability measure on the eigenvalues. And because you have this famous level of repulsion from the determinant, it's as if these eigenvalues experience a long-range logarithmic force. If you think of them as like a statistical problem, there's a long-range log force between them. And that leads to a very incompressible gas of eigenvalues, which gives rise to long-range correlations in the density of eigenvalues. You have a very incompressible gas, and so the pair correlation is very long-range. And that manifests here as this linear ramp. So basically, there's an early time part where it's kind of depends on the levels on the density of states. Then that early time part goes away. You have this linear ramp, which corresponds to the long-range correlation between pairs of levels. And then at very late time, you reach what's called a plateau, which is where you reach a time of order the nearest neighbor level spacing. And then there's no more states to correlate, and so you get this plateau behavior. Okay, but that's a random matrix. Physical systems are not random matrices, typically. How is this situation modified when you have a physical system? Let's go back to our spin chain. We say we have no other symmetries except energy conservation. Then, as I showed you, we expect energy diffusion to occur. And what that means is that there's going to be, at any given time t, in the thermodynamic limit, an extensive number of almost conserved quantities. Basically, there's a wave vector k sub t set by the time and the diffusion constant, such that all the modes with wave vector smaller than kt have barely decayed. They decayed by less than 1 e-fold, right? So they're almost the same as their initial value in the state. And if you count the number of such modes, you can easily see that it's extensive and proportional to the volume, and then this wave vector to some power. And my student, Mike Weiner, and I did this more carefully, including the correlations and transitions between these different almost conserved modes. And you can write down a very general formula which says that the spectral form factor should be enhanced by a factor which is related to the sum of return probabilities. That is the probability to start in this nearly conserved sector and transition back to the same sector after some time t. That sort of should make sense to you because I'm doing a trace, so it's natural to think about return amplitudes, and then because of the averages, it becomes return probabilities. And we can take, say, that theory of linear diffusion, energy diffusion, and we can do a calculation. We can calculate that return probability, and we get some precise formula involving that same factor of the number of modes here, and then the coefficient is slightly different. It's a zeta function at some value, but this is just a calculation you can do. So all we're doing is computing that return probability formula. I'm totally glossing over the details in the interest of time, but you can do the calculation and you get some nice answer. So this is like an enhancement to that linear in time ramp, which you can see at very late time, if t is very large, will decay to 1, but at earlier time is non-trivial because you have all these nearly conserved sectors. And nearly conserved means that there has to be very small matrix elements. And so the Hamiltonian is effectively like a bunch of disconnected blocks. Each block can be random matrix-like, but the set of blocks don't have level correlation. And so you would expect this enhancement. And some other people actually looked at numerics. And for some other spin chain, this time with a U1 symmetry instead of energy conservation. And what they showed in their numerics is that this expected formula that I wrote before for the case of one dimension, which is where they could look at it, describes the data reasonably well. So they actually exhibit data collapse as a function of t over L squared. That's like the diffusive scaling. And here I'm plotting log of the spectral form factor. They call it k divided by time. So this is just the coefficient of the ramp, taking a log, and this black curve here is that formula I wrote in the previous slide for the value of diffusion constant appropriate to their system. And their data from different sizes collapse onto this curve, so they argue it's a pretty good description of the spectral form factor at this hydrodynamic time regime. But I derived that formula in the case of linear diffusion. They derived it differently using some large dimension approximation, neither of which describes the actual numerics. And so you might ask, are there corrections to that formula? Can we derive it, more generally? What's going on? And so I'll just leave you with this one idea towards the end, which is that we can actually derive that formula using an effective field theory obtained from the effective field theory of hydrodynamics. So this is like a recent development in the last, say, 10 years or so, where people have written down quantum field theories that include hydrodynamic fluctuations, which describe the leading order hydrodynamic behavior, but also include the effects of these noise terms or fluctuation terms, right? And it's a sort of Schwinger-Keldysh or closed time path kind of field theory. It involves 2 copies of the fields. There's a lot of cool structure. I don't have time to go into the details of it, but these have been written down and understood as ways of sort of encoding the linear equations of motion, but also encoding fluctuations and looking at loop effects that arise from such fluctuations. This includes things like long time tails and other pieces of physics. And what my student Mike and I argued is that actually the 2 contours you have in these 2 different situations, in the hydrodynamic case and spectral form factor case, are actually very similar. In the hydro case, you have a state at time 0 and a boundary condition at future time, which encodes the trace. In the spectral form factor case, you have a forward contour and a backward contour, which are separate. But these 2 things look essentially the same, except for the boundary conditions in the infinite, well, not the infinite past, in the past and in the far future. Right? And so we argued that actually the same effective theory, the same hydrodynamic effective theory that governs this path integral, which computes hydrodynamic correlations, also governs special form factor, provided we modify the boundary conditions appropriately. So we change the boundary conditions so that the fields are now periodic in time. So it's an interesting kind of quantum field theory with time periodic fields, which is a significant change, but the action itself is the same. Right? So we're like modifying the measure, we're keeping the action the same. And what we showed is that you can then do the calculation of this path integral, at least in quadratic order. And the zero modes actually recover the ramp itself. So you actually predict this linear in time growth from the zero mode, including all of the random matrix factors, all the 1/2 pi's, which I didn't write out explicitly, but are all there. So you get exactly the random matrix prediction. And then if you look at the full path integral with all the non-zero wave vector modes, you exactly recover this return probability formula that I wrote before, which we derived just from quantum mechanics. So in other words, the argument is that this machinery actually predicts the ramp from the fluctuating theory of hydrodynamics and lets us compute the corrections to the random matrix ramp from the slow modes described with that same theory. And moreover, we can go beyond that and actually compute corrections, show that they're small in various situations, and help explain why that data from the numerics fits so well to the simple prediction of linear diffusion. Okay, so let me wrap up. What did I tell you today? I told you about links that the community is building between different, what I'll call manifestations of quantum chaos. So quantum chaos is still a vague concept. It's a slightly nebulous notion, but it has a lot of concrete avatars. And what I showed you today is that we can build interesting bridges between these different manifestations and connect them in very precise quantitative ways that actually help us, say, compute transport properties, or help us explain why random matrix behavior is so universal, because it just comes from hydrodynamics. There's lots of directions to pursue, including thinking about transport physics in 2D. That's a very big problem in condensed matter. We like to connect to other manifestations like eigenstate thermalization. And then I didn't talk much about black holes, but there are all kinds of interesting questions there. Like, for example, can we think about the event horizon as some kind of transition in the accessibility of information? Like the event horizon is this sort of teleological thing where you say, if I know the whole future evolution of the system, then there's this special surface which nothing can go past. Well, maybe that's like our return probability, or that's like our recurrence plot on the previous slide. As long as I don't do anything crazy like rewinding time, information never comes out. And maybe that's really what's happening at the horizon from the perspective of a general quantum chaotic system. Right. So there's all kinds of new questions and things we can ask, like, can there be a transition in my spin chain, which is like the horizon? And we don't know the answer to that question, but it's an interesting new question you can ask. And so with that, thanks. Sorry for going slightly over. Thanks for your attention.
Thank you very much. Let's thank Brian. Okay, are there questions?
Maybe I can. So about this breakdown of the random matrix theory description.
Yeah.
So if I remember right, like Berry also had some characterization of where, like in this semi-classical quantization picture, of where the random matrix description breaks down. And it had to do with sort of periodic orbits, the existence of periodic orbits in phase space and so on. And yeah. Is that related at all, or is it completely different?
No, it's definitely related. So one of the traditional ways of explaining this behavior is in terms of periodic orbits. And the linear in time piece comes because you're looking at correlations between two different orbits, an orbit and its time reverse. And you can always translate one of them in time and have the same correlation. And that's why you have this like time factor, this factor of t. Well, that's a little bit sketchy. Like you need to include some determinants and stuff, but anyways, it kind of works out in this way. And so yeah, like if you have like suppose for example you had a free particle system,
mm-hmm.
then you could translate not just the whole many body trajectory, but actually the trajectory of each particle individually in time. And this would predict, for example, a ramp which looks more like t to the n rather than t, where n is the number of particles. And we can actually see that. We did a calculation in an integrable system and saw that behavior. So yeah, I think there are all kinds of connections where if you have extra periodicities or extra correlations within your periodic orbits, then you get corrections. And so I don't have a like completely precise answer to your question, but I think it's definitely related piece of physics and a different but complementary way of looking at the same kind of physics.
Right, and so in order to sort of understand this breakdown, and here too, right, you say it's like you look at the longest wave modes first, or like, and those are the ones that sort of govern the breaking of this random matrix theory. Is that right? So if I sort of understand this low energy, these long wavelength modes, then I can sort of understand the breaking, right?
That's right. Yeah.
Okay.
Yeah, it's like you know, you have these all the long wavelength modes are almost conserved. So to zero Thor, your picture should be you have a Hamiltonian, which is a bunch of blocks, one block for each almost conserved sector. And so that would predict, just because the spectral form factor is a variance, so that means the variance would add. That's the usual behavior. So you would expect, you know, one factor of this ramp for every block. But the blocks are not perfectly decoupled. They actually have slow transitions between them. And eventually they relax. And so that's related to the return probabilities. Right. And that we can actually compute. That's a low energy, long wavelength piece of physics that hydrodynamics knows about.
It's because in some sense, the question I'm also kind of most curious about is also related to before that. So like the random matrix theory description in some sense is very universal, right? It almost doesn't care what the model is, except for whatever, some small number of parameters. And so then, but this breaking, presumably here you then start to see at least some of the specifics of the model. And I guess it's exactly the ones you're saying that enter into the hydrodynamic description, right? So
exactly.
Thanks.
Yeah, and there's like a really cool thing where, like if you go to this picture here, in this CTP, like closed time path formalism, there are perturbations that don't change the value of the path integral, which are these like antisymmetric perturbations that are the same, that are equal and opposite on the two contours. And in this modified version of the story, those actually are no longer irrelevant. Like they have an effect because of time periodicity. But if you go to long enough time where even the slowest mode cannot wrap the circle effectively, then you recover this invariance under this antisymmetric perturbation. And you can show that this change in the spectral form factor is exactly one of those kind of expectations. So it's just saying that once you go to long enough time so that all your modes are not wrapping the circle, then you recover the invariance of this theory, and that predicts that the spectral form factor is totally universal. You can make any change you want whatsoever to the Hamiltonian, as long as you keep the same symmetry class, and nothing will change. And then at earlier time, if there is a change, it enters via the diffusion constant or other heat capacity or other like long wavelength properties.
Any other questions? Well, I did have a question at the end of part 2, where you computed this plot for the diffusion. You said as long as you're at least in one dimension and away from integrability, we have good control. So what goes wrong? Well, integrability I can sort of understand, but could you say a little bit about what goes wrong, and also what prohibits you from going to say 2 dimensions?
Yeah, a great question. Yeah, so for integrability, like that's I would say, complicated subject, because there's, well, as you know very well, like there are many kinds of integrability, like it's not just one thing, but yeah, there could be like many more conserved quantities, or so like there's been a lot of nice works in the condensed matter literature showing for like XXZ chain, where you have lots of extra conserved quantities, that you can get the same kind of result by looking at what they call generalized hydrodynamics, where you include all the conserved quantities and like their slow variation. So I think it depends on the details more, but I think it can be souped up in principle to work there. So for the question about 2 dimensions, I think all the principles still apply. We think we know how to do it. It's just that the computational technology is much harder to work with. So these matrix product states, which underlie all this in 1D, are like super nice. They can be contracted efficiently. It's really, really good to work with them. In 2D, we kind of don't have the right data structure, so to speak, to do it effectively. We're thinking hard about this, very hard about it, but so far it seems like there's a boring abstraction, which is just we kind of don't know how to like represent the density matrix in a good enough way, or contract tensors in a good enough way.
I see. So it seems more like a technical problem than a conceptual problem in that sense.
Yeah, I think we have sort of we've understood a large chunk of the conceptual issues, and we have like a clear idea of what to do. There may still be a little bit more conceptual stuff in terms of how to represent things in the most efficient way, but yeah, I think a lot of the physics is understood now, or at least conjecturally understood.
Okay, thanks.
Yeah.
Any other questions?
Can I ask one?
Please.
Yeah, so again, about this thing of staying away of integrability, if you took like just an integrable model and you put something very small, it would still work, or like just some perturbation, like it would still work or not, like it's something easy to see, or like you'd break integrability, but
Yeah, that's a good question, but I'm not sure. I kind of worry that like one site or something is not enough, but yeah, I don't know. I mean, I have to say, like, for example, even like just take the Heisenberg chain, which is like our favorite, one of the favorite integrable systems. Like we have very little idea analytically what, say, the OTOC looks like in that system. Like we can compute it numerically using some technology, some tensor network technology. And it kind of grows, but not in the same way as like chaotic case. And it gets pretty large, but not like maybe to the maximum value. So it's just like actually totally unknown. I'd say it's a totally open problem to characterize OTOCs in like beta ansatz integrable spin chains. I think we just, as far as I know, we don't know how to do that. And it would be nice to know.
that's very interesting. Okay, thank you.
Yeah.
So actually, maybe maybe I don't understand. So if I take like XXZ and I stick in a random magnetic field, right? So this is like classic quantum chaotic spin chain, right?
Yeah.
And so presumably people have computed OTOCs in this. And so if I just turn off the magnetic field, are you saying that like presumably the numerical calculations do they suddenly get worse or something? I mean, I guess what, the desymmetrization or something?
Oh, I see what you're saying. Well, yeah, let me, yeah, that's a great question. Let me distinguish 2 kinds of numerics. So there's exact diagonalization numerics, where of course nothing goes wrong and you still do it. And then there are these tensor network numerics that my postdoc and I developed, where you can go to very large size and time. So we looked at like 200 sites and times the order of 200, which is far beyond what you can do with ED. And there we can most reliably capture the early time growth, but like describing what happens as you approach saturation, like the numerics seem to work pretty well. Like we did a lot of tricks and we pushed it, but I can't say we know really reliably what happens there. So at small size, they look like somewhat different, but it's hard to say exactly what the difference is. And at large size, they also look somewhat different, but we can't trust it in this like late time regime where they seem like most different. Yeah, so I guess I can try to like show you a picture maybe. Do I have a picture somewhere? Yeah, so I think the ED numerics, like, of course, still work.
So, but these tensor network methods are somehow very sensitive to like turning on or off that term in the Hamiltonian. somehow?
I would say somewhat more conservatively that we're not sure if they're very sensitive.
Okay.
But we can't say. Yeah, we can't say for sure, because that's a regime where where we don't have good control anymore. But I would just show you an example. So this is this little plot here. Can you see that? So this is free particles, which we can do perfectly well because the free particle operator stays in the one particle subspace. So it's actually trivial. You can exactly represent it with a matrix product operator. And so it works perfectly out to any time. This is Heisenberg. It still has growth. It has some wiggles. It's sort of saturating not to 2, but to something less than 2. Like 2 is the magic value that you normally get in a sort of strongly chaotic system at late time. The MPO gives you some other answer. So it's starting to deviate. There's these wiggles. We don't know what the wiggles are. There's this like less saturation. The MPO actually seems to be making it like more chaotic, pushing it towards the, presumably because it's erasing information about these like complicated conserved quantities or something. I don't know exactly, but yeah, so that's, and then let's see, is there a, I don't know if I have a good picture. This is what happens with the mixed field model. So you see it just grows and then saturates at 2, which is the like late time value you expect for a totally random operator. So yeah, I think so far as I know, no human knows how to calculate this or explain what's going on in this plot. So it's an interesting target.
And maybe also, so at the end, you were talking about the, again, maybe I didn't quite follow it, but the sort of the QFT that sort of describes the low energy modes, right, or something like this, where you're saying, so can you say simply what is that for, as you say, for a favorite model, like for XXX or XXE? Like, is it easy to describe?
This effective theory.
Yeah.
Well, yeah, it doesn't depend on the it doesn't depend on the macroscopics in that way. Like, so let me just show you. I kind of went through this too fast, but so here's the prototypical. No, it's not there. There it goes. So this equation is the prototypical Lagrangian, a quadratic Lagrangian for diffusion. Phi. So you can interpret the phis as related to time reparameterizations. Like it's very much like this kind of Euler versus Lagrange view of fluids, where you have the kind of internal time and the physical time, and you could think of dynamics as being about these maps from internal time to physical time. But anyway, so these are like maps between like some rigid time to the physical time, so fluid time to the physical time. So think of them as like time maps, and then phi a is the antisymmetric one, and phi r is the symmetric one. So there's like a field on the forward contour and a field on the backwards. And by seeing how these couple to the background currents, you can convince yourself that the energy density should be related to the time derivative of phi r. So that's just a calculation. And then this is what the Lagrangian looks like at the quadratic level. So if you ignore the phi a squared term, it's essentially a Lagrange multiplier that sets the equation of motion for the energy density. And then if you include this term, you can, for example, uncomplete the square. And then it looks like still a Lagrange multiplier that enforces some like fluctuating, like some stochastic version of energy diffusion. So it's basically like you take this equation, which is stochastic diffusion, where the noise has a certain correlation that is associated with making fluctuation dissipation work right and making energy conservation work. And you just add a Lagrange multiplier that enforces that equation of motion as an equation in the path integral.
Mm-hmm.
You integrate over, we're going to multiply or integrate over the noise, and that will bring you back to this.
Yeah. I'm still online. Sorry.
So that's the basic thing, and then like you have the diffusion constant here, which is the diffusion constant. Beta is the inverse temperature, and kappa is like the thermal compressibility. So just some simple, like why kappa appears, because that's related to the heat capacity, which is the fluctuation part. So that's why it's in front of the phi a squared, and then the diffusion constant is just the equation of motion.
So, like again, if say I was doing xxz with some random, so then d and kappa would depend on the parameters, like the couplings in the spin chain, right?
Yeah, they depend on the couplings. Yeah.
And so in some sense, so the way I know I'm doing xxz is basically because of d and kappa, right?
That's right. Yeah.
And then in principle, I suppose there could be like higher order terms, right? Like, I mean, this is the quadratic part, but in principle, I'm going to have some expansion, right?
Yes, that's right. There are all kinds of, at the very least, because d and kappa depend on temperature. So a local variation in energy density is like a local variation in temperature. So that will effectively generate vertices. And there can be other sources of interactions as well. And so, yeah, there are higher order terms. And in the usual theory, they're responsible for corrections to hydrodynamics, to linear hydrodynamics. And here they also give novel corrections. So like this formula I wrote here is corrected in powers, in higher order powers of 1 over t time by these vertices. So yeah, so in principle, like there's actually a more general answer here that we don't have full control over yet, but at least seems to be a small correction.
Okay.
And then if you really had integrability, no one's formulated in this way as far as I know, but you can imagine you have like a whole bunch of conserved quantities and different response parameters and fluctuation parameters, and you have some maybe more complicated kind of effective theory, which involves like a large number of conserved quantities. I don't know of anyone who's formulated in this language yet, but I think it could be done.
It's also for similar thing for like this, to understand this transition. If there you might you tune the parameters, you would expect to see somehow like it should go from this chaotic case to the to the integrable case.
Yeah.
So either they would somehow appear, or the coefficients, I guess, would go to 0 or something.
Yeah, I mean, I think we can describe lots of situations like this by including like almost conserved modes. Like, so for example, if you included something, if this d delta term, which is a constant, that would be like a mode that just has a at 0 wave vector, a constant decay rate, so it just decays. And those you can argue like also will affect things, but they damp out quickly. Like they're not slow. But if they are parametrically slow in some sense, you can include them into the theory and see how it modifies things. We've done a fair amount of that for different kinds of simple perturbations. Like for example, if you add a time periodic term to the Hamiltonian, then it converts it from this Hamiltonian random matrix class to a unitary random matrix class, like a circular unitary ensemble, for example, which has a different ramp, still got a ramp, but a different coefficient. And you can actually see how the Hamiltonian ramp crosses over to the integrable ramp, to the unitary ramp, and compute the corrections by including small like slow modes where you like are almost conserving energy, but the drive is slowly adding energy to the system, and you take that into account, and you can quantitatively reproduce the crossover. So if you have a long wavelength, like low energy, long time description of the crossover, I think you can probably plug it into this machinery and get a prediction for what the spectral properties will look like.
Yeah. Okay.
Okay, if there's no further questions, then I also have to go soon.
Yeah.
No problem. Thank you very much for the very nice talk. I really enjoyed it, and hope to see you again in person sometime.
Yeah, hopefully. Bye. See you all.
Bye. Thank